So I see that Štefan is already done with his presentation. So let me start this fifth lecture of a wonderful course given by Štefan. And today he will talk about non-Schurian, some small non-Schurian association scheme and coherent configurations. So the floor is yours, Štefan, please.
Thank you very much. First of all, I would like to warn the readers, the audience, that today's lecture will be not so educational on the first level, but maybe more on a research level. So what we already heard in the first 4 lectures, all the objects we were considering were Schurian. And now I would like to talk about association schemes and or coherent configurations which are non-Schurian. So just to recall what association schemes or coherent configurations are Schurians. Schurians are precisely those whose relations are 2 orbits of some permutation group. So if a coherent configuration is a Schurian, then I can find a permutation group whose 2 orbits are precisely the relations of these coherent configuration. And if there is no such group, then this object, this coherent configuration or association scheme is called non-Schurian. So first thing we have to notice is that that relations which are invariant under a group can appear just as 2 orbits of that group or as a union of suitable 2 orbits. So if we have a coherent configuration, then of course each of its relation is invariant under the group of automorphisms. So from this, one can easily see that each relation in a coherent configuration is either a 2 orbit of the group of automorphisms or a union of 2 orbits of the same group. That means that a coherent configuration is Schurian if and only if its rank is equal to the rank of its automorphism group. So by the rank of a coherent configuration, we mean the number of its relations, and by the rank of the group, of a permutation group, we mean the number of its 2 orbits. So if these 2 numbers are the same, then clearly all the relations are corresponding with the 2 orbits of the automorphism group. So the coherent configuration is Schurian. Association schemes are coherent configurations with 1 fiber. So if we have a Schurian association scheme, then it is clearly coming from a suitable transitive permutation group. That means that if we have the classification of transitive actions of permutation groups, then we have also classification of Schurian association schemes. So from this point of view, the non-Schurian association schemes are more interesting in a sense because they are not coming immediately from some action of transitive permutation. And the classification of these non-Schurian association schemes is quite hard even for rank 3. So if we have in the association scheme just two non-trivial relations besides the diagonal relation, then even in this case it is hard to classify all the non-Schurian association schemes. There were several attempts to go step by step from small orders. That means that there were attempts to classify all association schemes up to some order. At this moment, this classification is fully done up to order 34, and one can find it on the web page of Hanaki and Miyamoto, but also on that page you can find for several other orders complete enumeration or classification, and on that page you can find also the full description of the association scheme in the format of a color matrix, and also numbers like how many of them is Schurian, how many non-Schurian, how many symmetric, how many commutative, non-commutative, and so on. So the basic information is displayed there. The similar classification for coherent configurations is much harder because in the case of coherent configuration in general, we can have many more fibers. So the advantage of association schemes is that the number of fibers is just one. So similar attempts to classify or to catalogize all small coherent configurations were initiated in some bachelor or master thesis, first of all in Japan, where Shiratsuchi classified all coherent configurations up to order 11. After that, Nagatomo and Shigezumi classified coherent configurations up to order 12 and 13, respectively. And a little bit later on, Sven Reichard up to order 13. Unfortunately, their results were not agreeing one to other. So each of these guys obtained some other number for the number of coherent configurations. So it was good that we had some kind of classifications, but it was clear that we have to be careful. Not all of these results are accurate. And a few years later on, Matanzivav came with a little bit slightly new approach, and he was able to enumerate all coherent configurations up to order 15. So you can see that he finished his job just a few years ago, and with good computational technique, he was able to classify coherent configuration just up to order 15. So I think this displays how hard in general this problem is. So his result was widely accepted and published in Designs, Codes and Cryptography. I will give a precise reference later on. But if we join together the catalog of Hanaki and Miyamoto and this enumeration results by Matanzival, then we can create a table with the most important numbers concerning association schemes and coherent configurations. In a sense, for example, from this table, one can see that all the association schemes up to order 14 are Schurian. The first case, or the first order where a non-Schurian association scheme appears is order 15, and there is just a single one. After that, one can see that on order 16, there are 16 non-Schurian schemes, on the order 18, 2, again, on order 19, just a single one, and starting from 23, 24, the number of non-Schurian association schemes is quite big. Not so big, but if one would like to take them into hand and to play with them, it is a lot. So, and if we take the node number for coherent configuration, we can see that the number of coherent configuration is increasing not so fast, but even for order 15, it is almost 10,000. So it is a quite big number. And the first appears on order 14. And this observation or this knowledge became clear after the enumeration given by Matanzival. And from his enumeration, it was also clear that on order 15, besides the association scheme, besides the non-Schurian association scheme of order 15, there is one more non-Schurian object, but it has more fibers than one. So it is a coherent configuration, but not an association scheme. And one more observation, which is not visible here from this table I am showing you, but on order 15, the non-Schurian association scheme is not symmetric. But on 16 vertices, there are a few association schemes which are non-Schurian and symmetric. So I think in the first step, we can consider a symmetric non-Schurian association scheme because it is, in my eyes, much easier to work with than with other objects. So let us take the non-Schurian association scheme on order 16, which is generated by the so-called Shrikhande graph. This graph is, of course, strongly regular because you already know that symmetric association schemes of rank 3 are corresponding to strongly regular graphs. So it has 16 vertices. It is regular of valency 6. And to each pair of adjacent vertices and also for non-adjacent vertices, there are precisely 2 common neighbors. One usual description of this graph is to see it as a Cayley graph over the group Z4 by Z4 with connection set 0, 1, 1, 0, 1, 1. And in order to get a undirected graph, you have to take this connection set as with the inverses. So one can say or write plus minus 0, 1, and so on. So this graph looks like this. If I will embed it into a toroidal surface, then you have, if you are not familiar with the toroidal embedding, then this means that you have to identify this side with this side in the same orientation. That means that if you would like to know where this edge is going to, then it is written here, it is continuing here in this picture. And the same should be given with the remaining two opposite sides. And for example, this edge continues here, and this continues here. So we can see on this picture that it is a very nice graph. For example, I think it is not hard to see that it is vertex transitive. So if we would like to show that the corresponding association scheme is non-Schurian, then we have to see somehow that either the group of automorphisms is not transitive on edges or not transitive on the set of non-edges. So if at least one of these two things we will show, then we will have evidence that this graph is really non-Schurian in the sense that the corresponding association scheme is non-Schurian. For those who are familiar with the term of Latine square graph, you can imagine this graph as the complementary graph to the Latine square graph corresponding to the group Z4. This means that if you take the Latine square generated by the Cayley table of the group Z4, then each vertex of the graph corresponds to single cells in the table, and you are joining two vertices if they are occupied by the same symbol or if they are in the same column or when they are in the same row. So in this case, you obtain that, for example, this cell is connected to these three vertices, to these three vertices, and to these three. That means you are obtaining a regular graph of valency 9. And if you make the complement, then you are obtaining a graph which is regular of valency 6. And precisely this is the Shirikande graph. Okay, but let's go back to our task to prove that this graph is non-Schurian. So I will show that the set of non-edges is the right one to consider. So let us consider the pair of vertices 0, 0, 0, 2. So here, between these two, we don't have an edge. Just to recall you that I was defining this graph as Cayley graph with this connection set over Z4 by Z4. Now, from the definition of the strongly regular graphs, we know that these two vertices, 0, 0 and 0, 2, have two common neighbors, and it is not hard to see that they are precisely these two vertices. Also, on the second picture, the vertices 0, 0 and 1, 2 have two common neighbors. And now, if I'm thinking about whether these two common neighbors are joined or not, then in the first case, I come to the conclusion that their difference is 0, 2, and this is not in my connection set, so these two vertices are not joined by an edge in the graph. On the other hand, these two are joined because their difference is 1, 0, and this pair is living inside the connection set I defined. So this means that if there is an automorphism G sending this non-edge to this non-edge, then clearly this pair of vertices has to be mapped to this pair of vertices. But G is an automorphism, so the pair 0, 1, 0, 3 cannot be mapped, for example, to the pair 0, 1, 1, 1, because this would mean that I mapped a pair of non-adjacent vertices to the pair of adjacent vertices. This means that my graph cannot be Schurian because the group of automorphisms cannot be transitive on the set of non-edges. So this is, for example, one way to see that the Schrikhande graph generates a non-Schurian association scheme. There is also other way how to see this. May I ask somebody to switch off its microphone? Because it is...
It's done. Štefan, everything is fine now.
Okay, thank you. So there are many other ways how to see that this graph is non-Schurian. I will mention just one other, that if one consider again the pair of vertices 0, 0, 0, 2, then this pair of vertices are part of two co-cliques of order 4, or independent sets of order 4, while the pair 0, 0, 1, 2 appears just in a unique co-clique of size 4. So this is another way to see that the Schrikhande graph generates a non-Schurian association scheme. So this was one of the 16 non-Schurian association schemes of order 16. I hope you enjoyed this example. So now we can go back to order 15, where we already know that there is a unique association scheme. And we also know that that association scheme is not symmetric. To understand that association scheme, we will need the term of tournaments. So a tournament is just a complete digraph in which for each two different vertices u and v, precisely one of the darts uv or vu is present, not both. So for example, if you consider 4 vertices, then for each pair you in some direction put one dart and you are obtaining a tournament. Now, a regular tournament is such a tournament that if you consider every vertex, then the number of outgoing darts from each vertex is the same. Okay, clearly, since for each vertex the number of incident darts is n-1, this means that the number of incoming darts is n-k-1. And since each dart has to come to some vertex, then easy counting argument says that n by k should be the same as n times n minus k minus 1. This means that if we would like to have a regular tournament of valency k, then the number of vertices of such a tournament should be odd. Now, what I skipped here are some easy observations. By definition, one can immediately see that this matrix equation holds when I is the identity matrix of the corresponding order and J is the all one matrix. And this, since in A plus AT precisely the non-diagonal entries are precisely in one of the two matrices A or A transposed, then this clearly holds. In example 2, I am showing you a tournament which is, you can see that from each vertex there are 2 outgoing darts and 2 incoming darts. So this tournament is regular. But still, we are not finished with definitions. We need a stronger property of tournaments. We call a tournament doubly regular if it is regular and for each vertex V, the set of out neighbors span a regular tournament. So if I take all the out neighbors, then what I can see here is a regular tournament. I will use this example too. For example, I am choosing this vertex and it has 2 neighbors. Clearly, since it has even number of out neighbors, then the corresponding induced tournament will be not regular. So it has just 1 edge and 1 dart, and this is clearly not a regular tournament. So in example 2, we have a regular tournament, but not a doubly regular tournament. Maybe I have to show first a very trivial example of a doubly regular tournament. It's the oriented triangle. If you consider any of the vertices of the oriented triangle, then the set of out neighbors induces a regular tournament, and trivially regular because it has just one vertex and the valency is 0. So for example, the oriented triangle is a doubly regular tournament of order 3, but I would say that the second smallest example can be obtained as a Cayley graph over the group Z7 and connection set 1 to 4. Since I would like to obtain a digraph, I am not requiring now from the Cayley graph in order to have a connection set closed under inverses. So if you take this picture, then you can see that, for example, the vertex 0 has out neighbors 1, 2, and 4, according to the definition of the Cayley graph. It is clear that since it is a Cayley graph, then it is vertex transitive. So if I would like to check whether this tournament is doubly regular or not, it is enough to consider the out neighbors of a single vertex. So now I have chosen the vertex 0. So I would like to see what is going on the vertices 1, 2, and 4. So I see that there is a dart from 1 to 2, there is a dart from 2 to 4, and there is a dart from 4 to 1. So what is induced is a regular tournament, and I could see that cyclically that all the induced tournaments by out neighbors are isomorphic to the doubly regular tournament of order 3. But what is important that it is a regular tournament. So the full tournament is doubly regular. Okay. Now, by the definition of the doubly regular tournament, immediately follows that the number of vertices should be congruent to 3 modulo 4, simply because here you have a regular tournament. That means that the number of its vertices is odd, and by regularity it follows that also here you have the same number of vertices. So altogether you have 4 lambda plus 3 vertices. And also from the regularity and the conditions posed to the tournament being doubly regular, I don't want to say that it is easy to derive, but not hard to derive these 4 equations. The first row follows just from the regularity, and the equations in the second row from combinatorial interpretation and adjacency matrices of the corresponding objects. So what we can see from these equations is that if we have a doubly regular tournament, then the matrices I, A, and A transpose are forming a coherent algebra of rank 3. On the other hand, if we interpret all these conditions, then we can say more about doubly regular tournaments. If we have a doubly regular tournament on 4 lambda plus 3 vertices, then let's consider 2 vertices and such that there is a dart from x to y. Then the number of directed paths of length 2 from x to y, so in the similar direction than the dart between them is going, is precisely lambda. And in the opposite direction from y to x, the same number is, or for the directed paths of length 2 is lambda plus 1. And the number of common out neighbors of x and y is lambda, and the same holds for the number of common in neighbors. I found a few papers where this corollary is used for the definition of doubly regular tournament. So they are saying that, or they are defining doubly regular tournament in a manner that it is regular and the number of common, say, in neighbors of x and y is lambda. And from this definition, they can derive all those we have in this corollary and what we had in the definition. So these things are somehow equivalent. Now we are ready to explain the appearance of the non-Schurian association scheme of order 15. But in order to do this, we have to take a quite nice result which is a kind of a recurrent construction of doubly regular tournaments. In fact, there are many constructions for doubly regular tournaments. But I will show just this one, which is related to our object. So take a vertex. Clearly, it has some out neighbors and some in neighbors. And put here a doubly regular tournament with adjacency matrix A. Here put its transpose. Sorry, I may be missing. I would like to go to number 1. Yes, I am in BB. Okay, fine. And in between them, put the darts according to this rule that from here to here, you have copying the structure of the adjacency matrix A, and in the opposite order, the matrix A plus the identity matrix. And using matrix multiplication, you can derive that really the matrix created like this corresponds to a doubly regular tournament of order 2n plus 1. So exactly this is how we can obtain a double regular tournament on 15 vertices from the doubly regular tournament on 7 vertices, which was shown, I think, in example 3. So I'm not going to draw this picture because on 15 vertices it will be quite messy. So first we have to believe that this construction really works. And as I said, we can convince ourselves by matrix multiplication. But what is a little bit harder task is to see that it is really a non-Schurian association scheme. And oppositely to the previous example of non-Schurian object, here we have a non-vertex transitive association scheme. If you will draw at least pieces of these pictures, then you will see that if I will number the first vertex as number 1, then by definition, the set of its out neighbors induces a doubly regular tournament on 7 vertices. If you will draw the tournament which is induced by the set of out neighbors of the vertex 9, then you will find out that it is just a regular tournament, but not doubly regular tournament. So clearly, these two induced tournaments are non-isomorphic. Therefore, the vertices 1 and 9 lives in different orbit under the group of automorphisms. And from these, you can also derive that in fact, we have at least 3 orbits, because you can play the same game with the opposite darts, or by watching, by following how many neighbors from different orbits a concrete vertex has. So from this, one can see that really the resulting association scheme is not vertex transitive, therefore it cannot be Schurian. I hope it is enough to say this, because really otherwise we had to go to quite messy pictures. So this is how the smallest non-Schurian association scheme looks like. Now I will continue with the result, which is somehow joined with my name and my advisor when I was a postdoc, Misha Klin. So when I was his postdoc, he gave me this problem. We know that there are 2 non-Schurian association schemes on 18 points. And we would like to provide a combinatorial interpretation of them. So what is known, it is the color matrix from the catalog. This means that our input was or where these two matrices, which can be found in the catalog of Hanaki and Miyamoto. And the task is to reveal what kind of combinatorial object or how we can explain the existence of these two non-Schurian association schemes. So if you are given this kind of task, what you can do in the first step? For example, you can write down each of the relations from the association scheme. So in this case, let us take the scheme which has smaller rank, that is rank 6. So from the adjacency matrix, you can see that these two schemes have rank 8 and 6 respectively. So if you start to write down the, say, corresponding graphs to these binary relations, then of course the relation 0 is saying nothing because it's just a diagonal relation. If you take a look on the relation or the color number 1, then you can see that it corresponds to 3 cliques of size 3 and some other 2 factors. So again, it is just a collection of cycles. But if you take a look on the color number 2, then you are getting a cubic graph which is connected and it has 18 vertices. So in that case, what can you do? You can compare the resulting graph with the most famous cubic graphs on 18 vertices. And this strategy led to a success because it turned out that behind that color, the well-known Pappus graph is hiding. So that was some first evidence that, okay, this non-Schurian association scheme is probably nice, and it can be somehow joined to some geometries. And after that, we were able to explain the full picture concerning these schemes. But in order to do this, we needed the term of Byfine planes. So a Byfine plane, BP, consists of 2 copies of ZP by ZP, where P is a prime number, and these copies can be interpreted as points and non-vertical lines of this plane. So you can imagine points as in a standard manner by 2 coordinates, and also the lines you can imagine as in a usual sense, and the incidence between them again given in standard manner. This means that, for example, the Byfine plane B3 looks like this. You have 9 points. After that, you have a line, for example, 0, 0. This is 0, 1. This is 0, 2. And and so on. This is 1, 0. So you can interpret in this manner 9 points and 9 lines, and by term non-vertical we just excluded these 3 lines. So this object is called Byfine plane, and the purpose graph is the incidence graph of this Byfine plane. This means that, for example, if we take the point 0, 0, in this picture it is here, then it is incident to 3 lines which are going through this point. And it is easy to see that these 3 lines are having coordinates 0, 0, 1, 0, 2, 0, but you can check that all the other things are valid. So according to this observation, it was clear that one of the 6 relations can be described as an incidence between the objects in the Byfine plane. Now, it was remaining that how the other relations appear. And this could be also done using some auxiliary relations. In the set of objects in the Byfine plane, let's say this set will be omega, so it contains points and lines. So the first type of relation will say us that 2 points are in relation of type A when they have the same first coordinate and the difference between second coordinates differ by I, where of course I runs through Z3. This means that A0 will be a part of a diagonal relation on the points. A1 will be, for example, will contain something like this. So to xy, the corresponding pair will be xy plus 1. So this is in A1 and so on. So you can imagine. Similarly, you can do with the same job with for the lines. And also relations of type B when the first coordinates differ by I. So clearly here 0 is not possible, because if x2 minus x1 is 0, then I have a relation of type A. And similarly, it can be given for the pair of lines. And finally, I will say that point and line are in relation AI when this difference is I. In some sense, one can say that it is a distance between point and line, but I cannot say in fact the distance, because it is not a metric, because we are working on over the field Z3. So we can create the pairs between points and lines according to their distance, but now really you have to interpret distance just as on the picture. So it is not a real distance. And further, according to this relation, you can define the full diagonal relation. After that, you can put together into relation as the points and lines which have different first coordinates. and so on. So you can, in a sense, glue together those relations which were originally defined for points and lines, but they are in a natural correspondence. And using these relations, we can interpret the non-Schurian association scheme of rank 8 using these 8 relations, and the rank 6 can be obtained from the above, just going together U1, U2, and S1, S2. So using the Byfine plane and the finite geometry, we provided a computer-free combinatorial interpretation of the non-Schurian association schemes of order 18. But of course, here in these definitions, we are restricted for Z3, but the full job can be done also over Byfine plane of order P, where P is a prime. So I can repeat the full job for any prime number P. So after this understanding, we could extend our results for general P. And we could do this with the aid of the so-called Heisenberg group modulo P. So let's start from the scratch. Let P be a prime number. And for each such number, there is a permutation group which can be identified with the Heisenberg group modulo P, that is Zp cross Zp semi-direct product with Zp, so it is of order P cubed. And we let it act on the set of points and lines of the Byfine plane of order P. So one can generate this group by these relations. For example, simple translation of the plane, and here this corresponds to some reflection. And if we can imagine them on the points, how does it act on the points, then we can derive how does it act on the lines. And after that, we can consider the set of two orbits on the set omega. So and precisely the set of two orbits of this Heisenberg group coincide with the 6 type of relations we were defining in the case of the scheme of order 18. So we are obtaining these two orbits, and using these two orbits by gluing together some of them, we can obtain similar relation RSTU like in the original example, and also we can symmetrize the relations of type STU or put them all together of the same type. And now, using these relations, we can obtain many color graphs, but especially if we define one color graph using these colors, second using these, fourth using the third and fourth using these, we can prove that all these four color graphs are defining association schemes, and simply by counting the number of relations in them, their ranks are as shown in this item. So first of all, we would like to show how that these are really association schemes, and these can be done using the computation of intersection numbers. So since we have precise picture how the Byfine plane looks like and how the relations are defined, we can compute everything just using this information. So after computing the intersection numbers, we can see that these things are really association schemes. And as it was constructed, as the relations were constructed, it is clear that the combinatorial group of automorphisms of all these association schemes contain a subgroup isomorphic to the original group. And if the prime number P is at least 5, then all these four schemes are different and non-Schurian. For P equals 3, we had just two different. It was from the reason that one of these four schemes was Schurian because it has just very small rank. Two of them were coinciding, and so that meant that two of them are giving the same non-Schurian association scheme, and the fourth one was giving the second non-Schurian association scheme. So, but in general, we can define at least these four different schemes. And playing further with these objects, we could prove that the first scheme has as the full group of automorphisms the original group. The second and third have twice larger group, and the fourth one has 8 times larger group. And by the construction, you could prove this chain of inequalities where between just based on the construction, you can say that automorphism group of the third one is an overgroup of the automorphism of the second one. But if you are computing their size using the orbit stabilizer theorem, then you will figure out that really here there is an equality. So we could extend the full picture or the understanding of the two non-Schurian association schemes on 18 points to a series of non-Schurian association schemes of order 2p square. Moreover, there were interesting connections to known combinatorial objects, and I would like to mention just one of them. It turned out that we can, in the language of our relations, define by a suitable union the so-called Mackay-Miller-Shirane graphs. And these graphs play an important role in the so-called degree diameter problem, which is a well-known problem in the extremal graph theory. So your task for prescribed degree and diameter to construct the largest graph with these parameters. So this is degree or valency, and D is diameter. So in the table of the largest known graphs for special parameters, still the best ones are the McKay-Miller-Shirine graphs. So these play an important role there, and they were originally defined on the set of triples where the first coordinate is from Z2 and the other two are from ZP. And depending on P, whether it is modulo 1 or modulo congruent to 1 or congruent to 3 modulo 4, the adjacency between the vertices was defined like this. So I am not going to read their definition, but it is, I think, quite clear. Now, and for example, if you take P equals to 5, then the resulting graph is the Hofmann-Singleton graph, which is again a strongly regular graph with parameters 50, 7, 0, and 1. So quite nice connections were revealed, and for an interesting audience, I would like to refer to that paper where all these connections are mentioned. You can see that this paper has something like 40 plus pages, and it was in fact published just a few years ago. So this is how the story of non-Schurian association schemes of order 18 ended with. So it would be interesting to interpret more and more non-Schurian objects, association schemes, or coherent configuration, because really quite nice connections can be found. Now, here we have to touch the smallest non-Schurian object, which is a coherent configuration of order 14. And as it was a few times mentioned, it was discovered by Matanzivav using a computer search. And I don't want to go into details. I will show just the color adjacency matrix. From this you can see that it has two fibers, one of size 6 and one of size 8. And already the full story is published in the Journal of Design Codes and Cryptography. And I will mention just the key fact that everything is interpreted using the group SL23, that is the special linear group of 2x2 matrices of order 3, that is those which have determinant 1. So again, it is an interesting paper. And I am coming to my last slide for today, and I would like to connect today's talk with the next one by just mentioning what is going on the remaining small orders. So we are touching orders 14, 15, 16, and 18. And from the table, we could see that there is no non-Schurian scheme on 17 points. There is a single one of order 19, and also it is related to to a doubly regular tournament on 19 points. After that, there are no non-Schurian association schemes of order 20, 21, and 22. On order 23, there are 18 of them, and all of them are primitive and generated by, again, by doubly regular tournaments. Order 24 is much more interesting. The number there is 81, the number of non-Schurian ones. So a lot of job can be done there. And there is some relation between the orders 25 and 26 because at least in the case of rank 3, the strongly regular graphs can be connected. And during the next lecture, we will talk about one special strongly regular graph on 26 points, which is, in the terms of automorphism group, the most symmetric one, and that graph is known under the names Paulus graph, Rosenfeld graph, or Thomson graph. So we will call them Paulus, Rosenberg, Rosenfeld, Thomson graph. And that's all for today from my side. Thank you for your attention.
Well, thank you very much for the talk. It was very nice and very interesting. Please, questions to Štefan.
Štefan, I have just one comment. It's about the Shirkanda graph. You drew it on a torus with a square fundamental region. You identify opposite sides of a square to get the picture. If you draw it on a torus, but take a hexagon, yeah, that's the picture. Mm-hmm. Right, now you can get a more symmetric drawing by taking the standard triangulation of the plane and so you just draw a hexagon containing 16 vertices. And then if you identify opposite sides of a hexagon, you get the same torus embedding. It's topologically and combinatorially equivalent to this one, but not geometrically equivalent. But if you do that, it looks so much more symmetric, and you can see immediately that the group has rank 4 rather than rank 3. I don't know if shall I try sharing screen to see if I can show you a picture?
Yes, I will stop sharing and you are welcome to share your screen. Yes, I think at some moment I saw that picture, but it was years ago.
That's the same picture. Again, it's a Cayley graph for Z4 cross Z4. But if you look at the stabilizer of the vertex 0, it clearly has 4 orbits. There are points distant, graph theoretic distance 1, and then 2. But these 2 vertices at graph theoretic distance 2 are clearly in different orbits of the automorphism group, because the common neighbors of naught and W are adjacent to each other. Say the common neighbors of naught and 2A, which are this vertex and this vertex, they're not neighbors of each other. So it's immediately clear that the automorphism group of this graph, which is the same as the automorphism group of the map, has to have rank 4. And you can see the whole automorphism group here. You can see the dihedral group of order 12. It's much more visible than in the square picture. So that's my only comment. That was a great talk. Thanks, Štefan. I learned a lot from that.
Thank you very much, Gareth, for this, for pointing out this. I think I saw this picture years ago and I couldn't find it now. So thank you very much that you showed us it.
Well, I remember that we collaborated on a summer school in Slovakia a few years ago. And I think this picture came up at that time. That may be when you remember it from. Anyway, I'll stop sharing now.
Yes, it is possible. Thank you very much, Gareth, and I hope to see you again in some cooperation face to face.
I expect so. I'm still fairly active, so and you're very active. So. I believe you're giving another talk later this week, so good luck with that one.
Thank you.
Yeah, right. Yeah.
Just
in 1 week, one more talk. Yeah, it will be final one in the frame of this very nice, very interesting, and very important for our students course. Yeah, very important.
It's been an excellent.
Okay, are there any further questions to Štefan?
Yeah, can I ask a question?
Yeah, Akihiro, yeah, sure, of course.
Yeah, Štefan mentioned a non-Schurian association scheme on 15 points that was constructed by doubling the point association scheme, rank 3, right? So yeah, and this construction is generalized not only from 7 to 15, but any non-symmetric rank 3 association scheme, and then you get roughly twice the size non-symmetric one. So I wonder who discovered this construction? Do you know the history?
I think first mentioning maybe not precisely this construction, but implicitly that it is written in the paper of Dima Pasečnik, paper from '92. It concerns maybe I cannot see it now. I'm sorry for that. Yes. Skew symmetric association schemes with two classes and strongly regular graphs of type L2 and -1 and -1.
I see. Yeah. Such association scheme is equivalent to skew Hadamard matrices, right? So I wonder this is known to people in Hadamard matrices, but I couldn't find any reference. Maybe the Dima Pasečnik was the first to find.
I think this is well known for them because, or at least the connection between skew Hadamard matrices and the doubly regular tournaments.
Yeah, of course, that is already known to Del-South, but I wonder whether this doubling construction of Pasečnik is known to skew Hadamard matrices. I mean, Hadamard community.
I have no information concerning this.
Yeah.
Well, actually, it is interesting to get some relationships between these two approaches, right? Yeah.
Yeah. Yeah. Thank you very much.
Thank you. Thank you very much for your question.
Welcome.
Yeah. Any other questions to Štefan? Well, if not, then let us thank Štefan again for this very nice talk containing a lot of information. So I think that we will watch and rewatch this lecture again. And actually, we are waiting for the final lecture of this course because it will be like, well, a great mountain of this course. So thank you very much. And if there's no any other questions, further questions and comments, then thank you again. And we stop this lecture and let us come back in 1 week. The same time and the same Zoom connection and the same speaker here with us. Thank you, Štefan. Thank you.
Thank you very much.
Yeah.
Thank you very much.
It was very nice. Yeah, good.